All right, here we go. All right, now we're cooking. Well, welcome back. I believe this is the 6th week. Well, we're getting there little by little. Just a quick reminder. Today you have an exam. Some of you have started it. You have till 11:59. So again, as I stated before, give yourself plenty of time. Don't wait till 11:58. On average, about an hour. Now, it'd be comparable to last time. Now, that one has about 1, 2, 3, 4, 5 questions that I need to look at. So your final answer won't be there immediately. So I will get to them in the next couple of days. I get about 100 of these, no, 75 of these to look at. So I'll get to them right away as soon as I can. Okay. Any questions concerning chapters 4, 5, and 6? Any? No? All right. Well, if you do, feel free to jump in. We can ask some questions, but if not, I will continue with where we left off, chapter 7. Okay, chapter 7. Now here we've been talking about they're called Lewis dot structures. Prior to this page, we were doing some Lewis dot structures on some compounds. And basically, the steps are count up all the valence electrons that each atom brings to the table. Okay. Add them all up. I divide by 2 to give me pairs. You'll always be told what the central atom is. That means that everything else is bonded by some means to the central atom. We went through these examples, HCN and the CHF3 and so forth, okay? Now, once you know the central atom, bond all the other elements, whatever they may be, to the central atom, that takes care of a pair. And then whatever pair of electrons you have left, place them on whatever atoms you have to work with the exception, and like in the first example, hydrogen, because what you want to do is ultimately get to the point where all the atoms have the octet fulfilled. And hydrogen does not have the octet rule, it has the duet rule. We just can only handle 2 electrons around it. And then at that point, once you've taken care of all the pair of electrons that you have to work with, at that point, count the octet for each atom. If they're shy a pair of electrons, and start making double bonds. If that doesn't work, make triple bonds, etc., etc. Now, and we went through these examples here, okay? And count what I mean by the octet, which was a little bit of a confusing issue for some students. Let me just emphasize some aspects. Okay, let's take a look at the HCN example that's up here, okay? Now, if I just look at nitrogen itself, nitrogen has a total of 8 electrons around it. I got 3 pair that are being shared with the carbon. Therefore, they can count toward the nitrogen, and they also count toward the carbon. And then nitrogen has a lone pair. So total, there's 8 electrons around nitrogen. Okay, so that octet has been fulfilled. Now you look at carbon by itself, and you had a similar scenario in that 3 of those electrons, 3 pairs of those electrons are being shared with the nitrogen, and then the other single bond is being shared with the hydrogen. The result is that there are 8 electrons around carbon. Again, the octet has been fulfilled. And finally, if you look at hydrogen itself, it has 1 pair of electrons that are being shared with carbon. Therefore, its duet rule has been satisfied. Okay, so that's what I mean by looking at the octet of each atom individually, and keeping in mind that the bonded pair are being shared by 2 atoms and count toward each atom. All right. Then we did a specific example for HCN, and we did this one. We added up the valence electrons, 1 from hydrogen, 4 from carbon, 5 from nitrogen. We get that information from the group A that it's in. And so that can very quickly add up. You add up the numbers, you get a total of 10 electrons, which will be divisible, always be divisible by 2, whatever number of electrons you come up with. You'll see here in a couple of slides from now that if not done properly, you may end up with an odd number of electrons. That being the case, 1 or 2 things may have happened. One, you selected the wrong number of valence electrons to begin with, so go back and check that. Or second, you'll see here in a minute when we talk about the other compounds we're going to work with, you forgot to add or subtract an electron, but more on that later. So here we got 5 pair, and we're told that carbon is the central atom. Therefore, we can quickly draw carbon in the middle and then attach 1 hydrogen and 1 nitrogen on either side. And that takes care of 2 pair of the 5 pair that you calculated. And so you got 3 pair to work with at this point. Just put them wherever you want to put them, with the exception you can't put any more on hydrogen because hydrogen is happy. Okay, so I arbitrarily put them on the nitrogen. And so that line again denotes a pair of electrons. It's just more simple to write a line rather than 2 dots. If you use 2 dots, it's perfectly fine, not a problem. So we still have 5 pair, and so we haven't lost a pair along the way. So we double check, or nor have we gained a pair along the way, because you only have 5 to work with. So now at this point, you check the octet. Duet's happy for hydrogen. Nitrogen is happy because it's 8 electrons around it. However, carbon is not. There's only a total of 2 pair around carbon. So this is where you start making double bonds. And if that doesn't work, you continue to make triple bonds. Triple bonds is the max you can do. Okay, you won't find anything with 4 bonds, one like a quadruple bond. It's either single, double, or triple. Okay, and by playing with electrons, you end up with that particular structure. And you can see again that we got a triple bond involved between the carbon and nitrogen. Now at this point, you create or determine the general formula, and using the ABE notation for a general formula. And A is always there because that's the central atom. And B is the number of atoms bonded to the central atom, be it the same atom or be it a different atom. It doesn't make any difference, just the total number of atoms bonded to the central atom. In this case, we got 2. Okay, that should be a subscript 2. I don't have that function. So that's the general formula would be AB2. Now there's no E here because there is no lone pair on the central atom. So that's where we stop, and we pull up the shapes table. Let me make sure I get it. We go to the shapes table, and we search for the AB2, which happens to be the first example of the general formula. And that has a molecular geometry of 180 degrees. That's the geometry given there in that second column, which has a bond angle of 180 degrees, which its particular name is called a linear. Okay. So that's where we get that information. Notice if we go back to the formulas, for example, ammonia, that's the one in the bottom right corner, with nitrogen, 3 hydrogens, and the lone pair in the central atom. Its general formula would be AB3E with 1 lone pair. Using that information, going back to the shapes, we look for AB3E, which is this entry right here, second from the bottom of the table, of the column of the table, which has its name trigonopyramid and its bond angle, and that is the bond angle of in this case the hydrogens, being less than 109.5. All right, so that's how we're using the shapes table with the Lewis dot structures to come up with this part of it, this information concerning the molecule. Now, up to now, we've been doing neutral compounds. Notice there's no charge here on these, okay? Now, we're going to look at what are called polyatomic ions. Now, where are these at? Well, good old-fashioned periodic table. I told you I use it a lot. Going through the periodic table, on the bottom left corner, you see a table. This table lists some of the most common, what are called polyatomic ions. Now, what these are compounds that come together as a unit. And overall, they have a charge, either an anion or a cation. There's only one cation that we actually do a lot of work with, and that one's the one on the left-hand side. Where's it at? Come here. And that is the ammonium ion. Notice it looks like ammonia, the one we just did. However, that lone pair has been taken over with the hydrogen bond. So there are 4 hydrogens, and overall, it has a positive charge. Now, there's a multiple of other polyatomic ions that you may be familiar with that you use probably in everyday life or have used. This one here is called the hydroxide. Okay, that is a OH, has the whole thing, the whole package has a negative charge called hydroxide. You find this in things like liquid plumber. Liquid plumber is a sodium hydroxide solution. It's an alkaline, very strong alkaline. You also find it in some makeups they use to smooth your skin out. And what it does is it literally destroys and denatures the tissue on your face to get rid of that dead skin. There's some other ones here that could be confusing, but I'm going to try to unconfuse you here. Now let's take a look. Let's take a look at nitrogen. We got the atom, the element nitrogen, and we know that nitrogen is in group 5. And we know that also that it is a nonmetal. And so when it becomes ionic, it will gain 3 electrons. Being in group 5, it's got room for 3 electrons. So it has an overall charge of -3. Remember, we call that nitride, okay? Well, we can also take the same nitrogen and we can attach oxygens to it. And if we attach 3 oxygens to the nitrogen, we create a polyatomic ion called nitrate. And that's what that one is that I circled. There's 2 types. There's a nitrate, ATE, and then there's a nitrite. The only difference between the two is the nitrate has 3 oxygens and the nitrite has 2. And so here you got 4 types of 4 forms of nitrogen. You got nitrogen atom, you got the nitride ion, IDE, and now you got the nitrate and the nitrite. The nitrates you find quite a bit in foods. They use that as a preservative. Okay, you have the same scenario with sulfur. You got the element sulfur. Sulfur being in group 6 will gain 2 electrons to produce the sulfide ion. And again, if we bond it to oxygens, specifically 4 oxygens to that sulfur, we create the sulfate ion. And the sulfite ion is another example. The only difference between the two is, again, the number of oxygens. Okay. And then finally, another polyatomic ion is down here in the bottom, bicarb, sodium bicarb, otherwise known as baking soda, baking powder, baking soda. Okay, so those are the polyatomic ions. Now we're going to create Lewis dot structures of polyatomic ions. The procedure is the same. There's the only difference is this. Depending if it's either a cation or an anion, we're either going to add a pair or remove a pair of electrons, okay? Also, the other thing that we do differently is we put a bracket around the whole molecule after we come up with the structure. and that bracket, and then we put on that bracket a charge on the upper right corner of that bracket, and that designates the Lewis dot structure for polyatomic ions. So let's go back to that. So same steps. The difference is if the polyatomic ion is an anion, it has a negative charge. You saw that table, there's a whole bunch of negative charged polyatomic ions. We're going to add a pair of electrons. And the number that we add depends on the charge. Some polyatomic ions have a -1, some have a -2, some have a -3. So depending on the charge, we add that same number of electrons. If it's a cation, which really we only have one to work with, and that was the ammonium ion, we subtract a pair, okay? And then we put a bracket around the whole structure, and then in the upper right-hand corner, we put the charge of that polyatomic ion. Let's try the ammonium ion. So NH3 plus. We know it's an ion because we're told here it's got a plus charge, okay? Not to confuse that with NH3, which is ammonia, which is a neutral compound. So we have ammonia here. So we do the same thing like we've done before. We add up the valence electrons. 1 nitrogen gives us 5 valence electrons. 4 hydrogens gives us 1 valence for each hydrogen. So we have a total of 9 valence electrons from the atoms. And because it is a cation, we subtract 1 pair of electrons. So we now have 8 valence electrons to work with. And, excuse me, it gives us 8, and we have 4 pair, okay? So we got 4 pair to work with. The nitrogen is the central atom again. There are 4 hydrogens around it, so we can very quickly put nitrogen and just draw the hydrogens all the way around it, and we end up with this particular structure here, okay? And then we put the bracket with the plus charge in the upper right corner, okay?
I have a question.
Yeah, sure, go ahead.
So when we're doing this, we'll never hit like an odd number, right? It'll like whenever we get like an example, of this, like on like an assignment or the test or whatever, will it always be an even number? Will we always end up getting an even number?
Okay. Whether it is a polyatomic ion, it's a good question, or a neutral species, you always should end up with a even number or a number divisible by 2, okay, to give you pairs.
Okay,
now,
thank you.
The question that can happen is, like here we subtract 1 because it's a cation. What if you went the opposite direction and forgot, do I subtract or do I add? But let's say, for example, you got 5 and 4, and then you did a plus 1. So you end up with 10 electrons, correct?
Yes.
All right. Okay, so I got 10 electrons because I added instead of subtracted. I divide that by 2, I got 5 electrons paired to work with, okay? Now, if we look at that structure, it already has 4 pair. Is there anywhere on that structure that I can add that extra pair?
The central atom?
Well, the central already has 8.
Oh, okay. So yeah, then there's none. Okay.
There's none. You see? So that means that even though I had a number divisible by 2, I ended up with 5 instead of 8. I got an extra pair of electrons that I can't put any place. So that means that's a flag for you that says, uh-oh, I'm supposed to subtract and not add. Because you'll always have, if you tally up all the valence electrons and then correct for being a cation or an anion, you're gonna always have the correct number of electrons at the end. If you Okay, if you have a polyatomic ion and you have too many electrons or not enough, then the error went in subtracting or adding for the charge. Okay. Does that make sense? So that's a flag. So if you got too many electrons or not enough, then go back and check your math. Someplace, somewhere, something went amok. All right. Okay. All right. So let's do a few more examples. Okay. In this example, we have this. I realize you don't know what these are, VR03, and that's okay. We're just trying. Let me back up for a second. Now that we got the formula for the ammonium, we can do the same thing as far as the structure is concerned, because now we can still use a general formula. So we still have A, and we have B, and there's 4 around the central atom of nitrogen. So that's subscript 4. And so the general formula for this polyatomic ion is AB4, which when we go to the shapes table would tell you that that is, where do you go? Tetrahedral. Okay. So we can still use the shapes table for polyatomic ions so you can identify the geometry of that polyatomic ion, just like you can for the neutral compounds. Okay, so let's try a couple more examples. So we have this formula with BrO3. We got a negative there, so that indicates we got a polyatomic ion. Okay. And so now you got to be careful. Do I add or subtract? Add or subtract? We'll go back to your rules. If it is a anion, we need to subtract. We just did a cation. Did I say that right? If it's a cation, we subtract. If it's an anion, we add. Okay. So positive charge, negative number. Here we're subtracting an electron. Negative number, we add. Okay, so let's go back. So we add up the valence electrons. We have bromine brings in 7 valence electrons, no different from the neutral compound. The oxygens give you a total of 18 valence electrons. Now the fact that it's an anion, we need to add 1 pair because we got a -1 charge. So that gives us a total of 26 valence electrons, or 13 pair. Bromine is underlined, okay? So that is a central atom, so we can quickly draw 3 oxygens and bond 3 oxygens around the bromine in the center, and then put in, that takes care of 3 pair, and then we got 10 pair to work with that we place around all the atoms. And then we end up with a pair on the central atom. And so here you can count the pairs. There should be 13 pairs, okay? 13 pair, and then we put the bracket. The bracket is only for polyatomic ions, and then we put the negative on the top right corner. That indicates that it is a polyatomic ion. Now the general formula for this compound would be AB. This is no different than before. It's A, which represents bromine. And then we got B here that represents the 3 oxygens, because we got 3 of them. And then we ended up with the lone pair in the central atom, so that becomes E. So its general formula would be AB3E, which then we can go and look at the shapes table and look for AB3E, which is the second entry of the table. It's trigonal pyramid, and that bond angle is less than 109.5. Okay. There's a geometry, there's a shape, and there's a bond angle for the polyatomic ion. Okay, there's a question. That is correct, Nathaniel. All the dots there represent the electrons. Now, in my examples, I put a line, a hyphen. That hyphen represents two electrons. So you're welcome to put two dots, or you can put a line. It'll be sufficient. Okay. All right. Now, doing the next one, this is the sulfate ion. Notice that it is a negative Q charge. Okay. You can do the procedure again. We got one sulfur, which brings in 6 valence electrons, and we have 4 oxygens, which gives us a total of 24 valence electrons, because remember, oxygen is in group 6. 6 times 4 gives us 24. And then it is an anion, a negative 2 charge, so we add a plus 2 pairs of electrons to the valence electrons. That gives us a total of 32 valence electrons, or 16 pair. Okay, and so now we got sulfur in the center, and we can very quickly draw the 4 oxygens around the central sulfur, and then put in the remaining, in this case, 12 electrons, because 4 of them are taken care of by the bond. Now we could, as you go through this, also do check the octet. Make sure the octet has been fulfilled. You check to make sure you got the right number of pair of electrons, which in the first example we had 13, and here we have a total of 16. And then check the octet for each one, and notice that around that oxygen, and the same for all the other 3 oxygens, we have 8 electrons. And when you look around the sulfur, we have the 4 lines that represent 2 electrons each. That's the bond. It has 8, so the octet is fulfilled, and that is the formula, or the Lewis dot structure for the sulfate, the SO4 negative 2. We can also determine this general formula, which in this case would be AB4, okay, subscript 4. That is a general formula. You go to the shapes table, that is tetrahedral. Okay. Finally, the last one is CN negative. Again, that is called the cyanide polyatomic ion. We got 1 carbon. Now, in this case, there isn't a central atom. There's only 2 atoms, so either one could be the central atom. Okay. So right away, having just two atoms together like that should tell you this is going to be linear. There's nothing else bonded, just those 2 together. So 1 carbon brings in 4. 1 nitrogen brings in 5, and then it's a negative anion, so we're going to add 1 pair, which again gives us 10 electrons, valence electrons, or 5 pair. We put the carbon or the nitrogen and just put the electrons around, and we end up with that structure. Notice there are 5 pair around both the carbon and around the nitrogen. We put the bracket and the negative sign upper right corner to designate it as a polyatomic ion. Okay, and we can do the same thing in this case. It's only linear. It's only 2 species, so this structure would be linear. All right. Any questions so far? Yeah. All right. So now, earlier I talked about whenever you get, for example, the first BRO3, that you got a lone pair on that central atom. These lone pairs take up a lot of space, and so they would drive the other species, the bromine oxygen bonds, away because of the lone pair taking up space, more so than the rest of the electrons that maybe are bonded. And so this thing here called VSEPR, which is valence shell electronic pair repulsion model. basically is telling you what I just stated. When we get lone pairs of electrons, they tend to want to occupy a lot more space. Remember, electrons are negative charge. They're going to want to repel from each other. And because of this, they actually have a big impact on the overall shape of the molecule, okay? And we've been using the shape table. And the shape table that we've worked with so far is brought to you by because of these valence electrons and the way they repel each other and what effect they have. I already introduced to you the general formula of ABE, which is A is the central atom and B is the outer atom or whatever is bonded to the central atom. And then E represents a lone pair on the central atom. We don't care about the lone pair on other atoms, just the central atom, okay? And this is an example of something that's linear. The cyanide is another one. There's only two moieties here, two chlorines in this example, okay? That is the formula. There's a bond between the two chlorines, and each one has the octet fulfilled, okay? And so, in fact, all diatomic elements would have this. So they have a linear shape. Now the AB2 also is linear, okay? And it's linear because of the double bonds on the carbon and the oxygen. We did this example earlier. The thing also to remember is about electronegativity. We talked about that. Electronegativity, which is a measure of the affinity of an atom to pull electrons onto itself. So in the bonded pair. And so here we have carbon and oxygen. And therefore, the oxygen, because it's a lot more electronegative than carbon, will pull the electrons in that double bond onto itself. So it will pull them away from the carbon and toward the oxygen, okay? And that creates what we call a polar bond. There is a pole there because the oxygen, being more electronegative, is pulling electron density away from the carbon. It tends to give the carbon a little bit of a positive flavor, okay? We have a specific name for that here in a bit. The same thing occurs in the opposite direction with the other oxygen. Again, the oxygen on the left-hand side is a lot more electronegative than the carbon. So it too is pulling electron density from that double bond onto itself, resulting in a positive property of the carbon in the middle. Now, in this case, we have two polar bonds, but because they're pulling away from each other in opposite directions, the polarity of that bond, each of those bonds cancel out. And so the result is that carbon dioxide, though it has polar bonds, is nonpolar in nature because the polar bonds cancel each other out by the direction of where they're going. Let me clear this. This concept is important because it's we have to grasp one, electronegativity, and two, grasp in which direction that pull is going to, okay? We have a lot more to say about that. Another structure is AB3. This is a structure of CH2O, which is formaldehyde. Cancer-causing material. If you ever dissected a pig in high school, you probably smelled the formaldehyde. This is what they use it as a preservative. Anyway, this particular structure is called trigonoplanar, okay, with the bond angles of 120 degrees. Okay. The most common shape is the AB4 general formula, also called tetrahedral. A good example of this would be methane. Methane, here's the model to your right, the dark color here in the center is the carbon and the white are the hydrogen. Three-dimensionally, this is kind of a model of what it looks like. Now, the reason that has a bond angle, let me get an arrow here for a second, is there is interaction. Remember, this is a bond here, okay? And this is a bond full of electrons, two electrons, two electrons. The electrons want to pull away from each other. So in this configuration, that is the maximum distance they can be from each other and be fairly stable. And that maximum condition gives a bond angle of 109.5. And again, that's the most common configuration that we find out in nature for a tetrahedral. Now here we have the AB2E bent. Unlike carbon dioxide that was linear, sulfur dioxide is bent. And sulfur being in the different group brings in an extra pair of electrons. And again, we put a lone pair on the central atom right there, which is sulfur. Now we do have a pole here. Oxygen is a lot more polar. Excuse me, let me restate that. The electronegativity of oxygen is greater than that of sulfur, okay? Because oxygen is right next to fluorine, so it's a lot more electronegative. So they tend to pull the electrons toward itself much more than sulfur. And there's a pull in two directions here in both sulfur-oxygen bonds. Unlike carbon dioxide, where the pull is in the exact opposite direction and they cancel each other out, because of the lone pair, that bond angle is changed to be much less than 120 degrees. Therefore, the pull of those electrons are not canceled out. That the polar bond, which we'll have more to say about here in a bit, do not cancel each other out. They're in opposite direction, not completely opposite direction like carbon dioxide, but the result is that we end up with a polar molecule. Okay. One thing to put in long-term memory is that whenever you end up with a lone pair in the central atom, you can unequivocally say, I got a polar molecule. Okay? Polar molecule. All right, so, and then we have this example of ammonia. We did that before. We end up with a lone pair on nitrogen, central atom. Automatically, I got a polar compound. Okay, and again, because that lone pair being a central atom is causing that bond angle to be much less than the typical tetrahedral bond angle of 109.5. Again, because those electrons are occupy a lot more space than the bonded pair. Water has two lone pairs, really making it very polar. In fact, water is the most polar solvent that we have. And we have here oxygen with two lone pairs. That bond angle is really much, much less than 109.5. Again, because of the lone pair. So the lone pair, the electrons repulsing, having a repulsion for each other results in defining the structure of the compounds. Okay, so to summarize all this, be able to draw the Lewis electron dot structures, okay, of any covalent molecule or polyatomic ions that you should be given. And then from that structure, using the general formula and the shapes table, you should be able to determine the shape and the bond angles, okay? So you haven't downloaded the shapes, please do so. You're going to use that quite a bit. And you may want to practice trying pH 3 and try ozone. Ozone, that is the formula for ozone. We're all familiar with ozone. You know, we get an ozone warning. There's two types of ozone. Structurally, they're the same. But the ozone around us that gives us all the breathing problems, that's the bad kind of ozone that hangs out here in the atmosphere that we're breathing. Good type of ozone is up in the atmosphere, very high up in the air. It's a very thin layer. And what that does, it protects us from the generation of the UV lights from the sun. In fact, without it, we'd be bombarded with a lot more UV lights than we are now. We do have a problem, though. That ozone layer up there has got a little bit of a hole, actually a pretty big hole. So that's causing some problems with too much UV radiation being bombarded onto the earth. We all know that the sunlight long-term use can cause things like cancer, but it can also affect plant life and all kinds of problems. So ozone. So try those two structures and bring them back to class. If you can't figure it out, we can definitely talk about it. But it's challenging. At O3, there's 3 oxygens that are bonded to each other. So see what you can come up with a structure. All right. So, which brings us to bond polarity, which I introduced to you already. Okay. Now, we have two types of chemical bonds. Now, remember the first one was called ionic bond. Anybody remember what was the criteria to have an ionic bond?
That they have to be different.
Opposites attract.
Yeah.
It has to be a non-metal and or a positively
Non-metal
charged
and
metal
a
and a negatively charged non-metal.
You broke up there, but I cut the non-metal. Was there something else?
Sorry, I might be the internet. I was saying that there was a positively charged metal and a negatively charged non-metal.
Non-metal, yeah. Now, I don't know if it's from my end, but I think what you said was a metal and a non-metal.
Yeah.
Correct. Okay, there you go. And so that's the criteria for a ionic bond. And so the other aspect about an ionic bond is the negative anion and the positive cation have a full-fledged charge. So they come together like two magnets, okay? And that's how, in solid form, that's how they are, because of the attraction of the full negative and the full positive charge. Okay. Covalent bonds, that's not happening. Now, one more aspect about ionic bonds, ionic compounds, is that you can take ionic compounds and dissolve them, put them in water, and they dissociate into their ions, totally dissociate. Now, some dissociate 100%, some dissociate maybe 5%, but all of them, all the ionic compounds will dissociate to some extent, from a lot to not so much, into their ions. Okay. Now, with respect to covalent bonds, there's an actual sharing of electrons. There's an actual true bond. I cringe every time I hear ionic bond because it's not really a bond. It's more of an attraction, electrostatic attraction. But the textbooks continue to use the term bond, so we'll leave it at that. Whereas covalent bonds, that is a true bond. That is a pair of electrons being shared between two atoms, okay? And we have two types of sharing. One type is equal sharing, and the other type is unequal sharing, okay? And depending on the atoms, it would tell us which ones would be equal sharing and which ones are unequal sharing. The ones that are shared equally are called non-polar bonds, meaning that there's no pole. You know, the Earth is a pole. You got the North Pole and the South Pole. Your battery in your car, your electronic device, whatever you're using now, has a pole in it. The battery has a positive side and a negative side, okay? A non-polar bond does not have that. It is two atoms that are bonded together, and they happen to be the same atom, and therefore there's equal sharing between those electrons, be it a single bond, double bond, triple bond, okay? Now, when there's unequal sharing, it creates a pole because one side is pulling more of the electrons toward it. So it's giving it more a negative character than the other side. It is dissipating the negative character on the other side. So it's creating a temporary positive side and not a temporary, but a positive side and a negative side. But it's not a full-fledged negative and a full-fledged positive like in ionic bonds. Okay, we have a symbol to represent. It's really what we call a partial positive and a partial negative. Okay, and so to distinguish right away, you know, if you look at a bond, the first thing you determine that it is covalent bond, and that is the combination of two nonmetals. So the next thing is the subcategory is, okay, is it polar or nonpolar? Well, if it's nonpolar, the two atoms are the same. If it's polar, then the two atoms are not the same. Okay, it's that straightforward. For nonpolar, you know right now 7 examples of a nonpolar bond, and that is all of the diatomic molecules. Have no fear of ice cold beverage. Okay, those diatomic molecules are the same atom, so that bond between them is equal shared bond. Therefore, they are nonpolar. I'm going to add one more on top of that. So for nonpolar bonds to be all diatomic, okay, plus any carbon hydrogen bond. So now you have 8 examples. Carbon hydrogen bonds are all considered nonpolar, even though the atoms are different. And they're different because the electronegativity of carbon and hydrogen are essentially the same. So they're treated as nonpolar. You have around you examples of carbon-hydrogen bonds that are nonpolar. Vegetable oil, lard, these are all carbon, not all carbon, the majority of those molecules are carbon-hydrogen bonds. We know that oil and water don't mix. The oil is basically a lot of carbon-hydrogen bonds. They're very nonpolar, okay? So all diatomic. So you're aware of 8 examples of nonpolar bond. That means that everything else is polar, okay? Everything else is polar because, oh, let me erase that, because there is a difference between the electronegativity of 2 different atoms, okay? And remember the trend of electronegativity. Fluorine is the most electronegative atom out there, element. And so we use that as our benchmark. So if we're comparing the electronegativity of, say, 2 different atoms, like carbon, nitrogen, we find their position in a product on the periodic table relative to fluorine. And the one that's closer to fluorine is the most electronegative. That means for that bond, it's going to pull the electron density toward the most electronegative species in that bond. And so that's to refresh your memory on the trend. Left to right increases, bottom to top increases. Fluorine is our benchmark, okay? And so I just mentioned the nonpolar examples, all the diatomic molecules, plus the carbon-hydrogen bond, okay, are considered nonpolar. Now, with polar bonds, it has to do with electronegativity. So if we look at carbon-oxygen bond, that example there, that's C-O, okay, well, that's a polar bond. We got 2 different elements there that are not carbon-hydrogen. The next one, HCl, 2 different elements, polar. SF, sulfur and fluorine. Again, polar bond. Silicon and nitrogen bond. Again, a polar bond, okay? That means that one of these atoms is going to be pulling the electrons onto itself. And we designate that by using what are called the polar arrow and this what is called partial positive side and partial negative. That's denoted by the symbol lowercase delta. Delta is a Greek symbol, which generally means a change, but that's delta, lowercase delta. The uppercase delta in Greek is that triangular symbol, okay? So lowercase delta. We have a partial positive and a partial negative. So if we look at the first example down here, with carbon fluoride bond, okay, the first thing you do is to see which one is more electronegative. Well, we know that fluorine outbeats everybody. So fluorine is the most electronegative. Therefore, we draw an arrow pointing toward fluorine from carbon, and we put a little plus sign on the carbon side. That tells you that on the carbon side has what is called a partial positive side, and the fluorine has a partial negative side, okay? Not a full-fledged like the ionic compounds, but a partial, which is a good thing for us in organic chemistry. As a synthetic chemist, one of my jobs was to create compounds, new compounds. Some of them had pharmaceutical use, some did not, some for a variety of reasons. But when we looked at a compound, we always look for points that have polar bonds, because with that partial positive, I can add, because of that polarity, that's where my reaction that I want to create would occur because of that differential in charge, okay? And if you can think about this, if I had another molecule that would line up with this, I would have my partial negative would line up and be attracted to a partial positive, and so forth, okay? That interaction, in other words, if I were to draw another molecule of CF, like that, okay? There, let me clear some of this. And if I had another molecule set up like that, there would be an attraction going on here because of the partial negative. There'd be an interaction going on between the molecules because of the partial negative of the first one and the partial positive of the next one. And that is what causes things to, say, boil at whatever temperature, because those interactions between molecules can be very weak or they could be very strong. Water molecules, those interactions are very strong between the molecules. Hence, that's why water boils at 100 degrees Celsius. It takes that much temperature. But if you take ethanol, it boils at about 78 degrees Celsius, much lower, because that interaction between molecules is totally much less. But much more on that later on. But all that's related to electronegativity and the polarity of the molecules, okay? All right, so carbon fluoride, we draw an arrow from left to right. The partial positive is on the carbon, the partial negative is on the fluorine. With OH, again, it's a polar bond. We got two different atoms, definitely polar, okay? If you look up the electronegativity, we know that oxygen is a lot more electronegative than hydrogen based on their position relative to fluorine. Therefore, the partial arrow, the arrow goes from right to left, okay? Because the oxygen is pulling that electron density onto itself, more so than hydrogen is. And then finally, the phosphorus and the chlorine, in this case, chloride bond, okay? The arrow's going from left to right. Again, because of the electronegativity of chloride, which is much greater than the one of phosphorus. So we create a partial positive on the phosphorus and a partial negative on the chloride. Now, you probably, how this affect? You know, you may have one time taken a balloon, rubbed it on your head, right? And then placed it on your chest. It stuck, did it not? Why would it stick? Why would it stick? Why would that balloon rubbed on your head stick onto your shirt?
Friction.
Not quite.
It's static.
Static, okay, you're getting there. Static, okay. It's definitely not heavy powder stuff, right? It's no magical stuff. Okay. I want you to think about this for a second. You rub that balloon on your head. Your head, I told you before, we got electrons all over us. Okay. Some of us have a lot of electrons on our head. You know, you wake up some day and you got this bad hair day, right? Boom. Well, you can get a balloon, rub it on your head. You transfer those electrons that have a negative charge onto the surface of the balloon. I got a video that will demonstrate this. Okay. Now, once you do that, you bring that balloon onto your chest. Now, on the surface of your chest are electrons. They're there. And so you got a balloon coming at you, and it interacts with the balloon, with the electrons on the surface of your chest. Well, you got negative and negative. What's going to happen to those electrons on your chest? They're going to be pushed away to go into your body much more than the electrons of the balloon. The result is you have a partial positive area on your chest. You have a partial negative area on the balloon. What's going to happen? Just like magnets, they're going to attract each other. And the balloons stay there for a short period of time till the electrons dissipate and everything goes back to equilibrium. Okay? Well, that is like a temporary what we call induced dipole. Okay? The nonpolar molecules will do something similar, and we'll get to that with time. But that interaction, having a partial positive and partial negative, is what I'm saying is occurring with these molecules, these bonds here in these examples with other molecules, which then affect the properties of boiling point, surface tension, viscosity, things like that. Okay? Some of these properties are very weak, some of them are pretty strong. But it's all about electrons. You know, I told you before, electrons that's where all the action is, chemicals occurring. Here we got again going again. It's all about electrons in the bond and how they behave, with one atom pulling more electrons onto itself, causing a dipole. Okay. All right. Right, so we know about noble gases, okay? They're not going to do anything really. They're inert. That's why we call them noble gases. They're not going to react. But as a side note here, those big, giant noble gases, FYI, not for Chem 130 information, but general information, the big noble gases, because those electrons are so far away, they will cause some reaction. But for 130, they won't react. We know that fluorine is the most electronegative, the electron hog, okay? It wants to pull electrons onto itself very tightly, high electronegativity. One reason they use it in fluoride, they feel that once incorporated in your teeth, it can create very strong bonds. Okay, so here are some example questions where they may ask you, add the delta notation, that is the partial positive, partial negative, and then to add the polarity arrow, okay, with the arrow goes in the direction of who's more electronegative. So we got an example here, carbon and oxygen. What do we do first? We go to the periodic table because we don't have to memorize the electronegativity values. Electronegativities are an actual value. And if you want to sit there and measure and memorize 118 of them, okay, go ahead. Or you can just learn who's more electronegative than the other based on its position of fluorine. And then that tells you which direction you're going to put the polarity arrow and where you're going to put the delta notation. So if we look up carbon and we look up oxygen, we know that oxygen is closer to fluorine. Therefore, it's a lot more electronegative. Therefore, I can draw my arrow from left to right, okay? And I can put the partial positive on the carbon and the partial negative on the oxygen. The next example, I got nitrogen and fluorine. I don't have to look this up because I already know, right, that fluorine is the most electronegative. So electron density is going to be pulled toward the fluorine with no question. So my arrow goes from left to right in this scenario. Partial negative on the fluorine, okay? Here we have oxygen and hydrogen. Again, oxygen is a lot more electronegative. And so the arrow in this case, because that's the way the bond was presented, goes from right to left, okay? With delta being delta positive on the hydrogen and delta negative on the oxygen. Now on chlorine and carbon, which one's more electronegative? Find in the periodic table, chlorine, or in this case chloride, is a lot closer to fluorine than carbon is, okay? Even though chlorine is one group down, carbon is 3 to the left, right? 3 to the left, 3 columns to the left of fluorine. So chloride is a lot more electronegative, so our arrow goes from right to left. As a general guideline, the halogens, that's group 7, always win the tug of war with respect to electronegativity. All right. Now, how about this one, carbon, hydrogen? How would I write this one? Anybody want to take a guess? Would I go right to left, left to right?
Right to left?
Okay, I got one right to left. Do I hear left to right?
Left to right.
I got one left to right. Do I hear none?
None.
Okay, none. None is correct. Remember, the 7 diatomics were
Dude, I
nonpolar.
was gonna say none.
Oh, is that what it is? Okay.
I didn't know there was an
There you
option
go.
for none.
None. Okay. It's not
All right.
polar. It's one of the 8. Remember, you got the 7 diatomics plus carbon, hydrogen. Okay?
Might be Mr.
They're
Dwarf.
very nonpolar. There's no polarity involved. Nonpolar,
I'll go cry.
Oil-like, just like vegetable oil. Okay?
Thank you, sir.
All right.
I'm gonna go
No
cry
problem. Okay, go cry. Okay. Now, here's a question. They're asking you 3 things here. Okay. Are the bonds ionic? Okay. Then if not, are they if they're not ionic, they must be covalent. And if they are covalent, which ones are polar and which ones are nonpolar? Okay. And so we said earlier the criteria for an ionic bond was a metal and non-metal. And so which one is an ionic bond here?
NaCl.
Exactly. NaCl, otherwise known as sodium chloride, otherwise known as what you put on your French fries, okay? Good old sodium chloride. So that's the only ionic compound. So covalent compound polarity doesn't play a factor there, okay? Now let's look at BR-BR. That means that everybody else is a covalent bond. That's good. What about BR-BR? Is that polar or non-polar?
Non-polar.
Exactly, non-polar, because we have 2 elements that are the same. That tug of war in that line that represents the bond is equal. Okay? So, PF, phosphorus and fluoride. Polar, non-polar?
Polar.
Polar.
Definitely polar, extremely polar. And the same would be true for fluoride and bromide, okay? And so here we have only one ionic compound. And then the other three are covalent. Of those covalent, the bromine is nonpolar, and the bromine fluoride and the fluoride bromide are both polar, okay? All right, so the thing about polarity is it's going to come again over and over again in the subsequent chapters. And so let's not forget about it because you'll be using it again. It's just look at it as a tug of war in the bonding electrons. Now, one of these is going to be pulling more electrons than the other, giving you a polar bond, which then would affect the properties of that molecule. Okay? So, and don't forget, carbon, hydrogen, nonpolar. All right, so here, I think
Can you go back really quick, please?
yeah. Okay. So
Thank you.
it's
Sorry, I just wanted to screenshot it.
yeah, no problem. It's a tug of war in covalent compounds. Okay.
Yes, sir.
Ionic compounds, no tug of war. They just separate once you put them in solution. All right, here they're asking you to give you ionic to determine what's ionic, what's polar, and what's nonpolar. I think we can very quickly mark the ionic compounds, right? Because we're looking for any metal, non-metal combination. We already talked about sodium chloride, all right? What about potassium and oxygen? Would that be ionic? Yep, right, because potassium is a metal. Oxygen is a non-metal, just like sodium is a metal, and the chloride is a non-metal. So that is ionic. Remember that, okay? That implies that everybody else here has to be covalent because there's no other combination of metal, non-metal combination. All right, of the covalent compounds, we can quickly look at the ones that are the same. Hydrogen, hydrogen, okay? That would be classified as a nonpolar right off the bat. Do we have another one where the two atoms are the same?
Oxygen, oxygen.
What? Oxygen, oxygen. So that would be nonpolar. Can we think of another nonpolar bond here?
Carbon. Hydrogen.
Hydrogen.
Carbon, hydrogen, exactly. Okay. And so the squares here represent covalent bonds, but nonpolar. Okay. So that means that all the rest of them, HCl, this is something you should be familiar with quite a bit because it's running around in your stomach right now. That's called hydrochloric acid. Okay. We got a hydrogen and a chloride, two dissimilar nonmetals. Therefore, you have a polar bond. You have chloride and carbon, two dissimilar nonmetals. Again, you have a polar bond. And then finally, you have the phosphorus and the fluoride. Again, two dissimilar elements, and therefore you have a polar bond. Okay, so ionic,
Wait.
polar covalent, non-polar covalent, polar covalent, non-polar covalent, non-polar covalent, ionic, and polar covalent. Now,
I
being
have a-
able to,
I have a question.
pardon me? Sure, go
Um,
ahead.
So for the potassium and oxygen, how is it ionic again? I don't know
It's
why.
because- Okay, who can answer that question?
What was the question?
The question was, how is potassium and oxygen ionic? Because remember the criteria for being ionic was a metal and a non-metal.
Potassium is the metal.
Yep, so potassium is the metal and the oxygen is the non-metal. Therefore, ionic. Okay?
Okay. All right. I don't know why I had a brain fart.
It's okay. Just remember metal, non-metal, ionic. Non-metal, non-metal, covalent. And then within subcategory of covalent, it would be polar, non-polar. Okay?
Okay. Thank you.
All right, no problem. So once you are able to determine just by looking at the bond whether it's ionic, polar covalent, non-polar covalent, and then knowing the structure based on the Lewis dot structure, you'll be able to determine whether the whole molecule is polar or non-polar. Okay, so it's all tied in. And once we know about who's non-polar, who's polar, then we go into, down the road, we talk about intermolecular forces. And those are the interactions I introduced. I told you when we had that partial positive, partial negative, how because of that, the molecules can interact with each other based on the partial negative of one and the partial positive of the other. They interact. There's only 4 types of forces that describe that interaction, that then define such things as boiling point and vapor pressure and viscosity and surface tension. Okay, so you see we're kind of building up, and once we get this going on, then we're going to be talking about reactions and whether reactions are feasible or not. So based on knowing our polarity. All right, so I think I got, let me clear this out. I think I got about 3 more minutes. So let me finish this up here real quick. Molecular polarity. Now we talked about the bond itself being polar or non-polar. Now we're taking it up to the molecule itself as a whole. Okay, so here's some general guidelines. If all of the bonds in that molecule are non-polar, then overall the molecule is non-polar. Okay. Now, if there are polar bonds in that molecule that do not cancel out, then you have a polar molecule. And we had the example of the sulfur dioxide, where you can see those arrows don't cancel out, because even though they're going opposite direction, mathematically, they're not going in the exact opposite direction like carbon dioxide was, okay? When the polar bonds do cancel out, like carbon dioxide here, then you end up with a non-polar molecule. All right, so the point here is, yes, you can have a non-polar molecule with polar bonds. Carbon dioxide is an example. All right, so something to talk about. Carbon, hydrogen, that's methane, all non-polar bonds, okay? Boom, non-polar molecule. Now, carbon tetrafluoride, trifluoride, fluoride. If you recall, we did the Lewis dot structure of ammonia, NH3, and we ended up with a lone pair in the central atom, okay? Now, phosphorus is in the same group. And if you go through the same exercise, you're going to end up with a lone pair on the phosphorus. And so just the fact that you got a lone pair on the central atom tells you you have a polar molecule. Because those molecules in that, those bonds, polar bonds in that cancel out due to the lone pair. Carbon dioxide we talked about, polar bonds cancel each other out, therefore you have a nonpolar molecule. Okay? So we did water, we did ammonia. You might go back to refresh your memory to draw the Lewis structure, determine the shape, the bond angles, and determine if the bonds are polar or whether the molecule is polar. You might do that there on your side. That being the case, ladies and gentlemen, guess what? Another one bites the dust. Okay. All right. So if you haven't done your capsid, good luck. Keep it simple. Don't make it more complicated. We're not trying to confuse you. All right. So keep it simple. Give it your best shot.
All right. Thank you.
Thank you, sir.
Okay. Thank you. You guys have a safe, stay safe out there. I'll see you Thursday.
Thank you.
All right.